Good afternoon, and welcome to the Center Stage Seminar Series event. My name is Tiffany Willoughby, Education Programs and Outreach Manager in the Office of Research at the University of Texas at Dallas. I will be your host. Joining me today is Dr. Reza Moheimani. Reza Moheimani currently holds the James Von Eyre Distinguished Chair in Science and Technology in the Department of Systems Engineering at the University of Texas at Dallas, with appointments in the Electrical and Computer Engineering and Mechanical Engineering departments. His current research interests include applications of control and estimation in high-precision mechatronic systems, high-speed scanning probes, microscopy, and atomically precise manufacturing of solid-state quantum devices. Dr. Moheimani is a Fellow of IEEE, IFAC, and the Institute of Physics in the United Kingdom. He is a recipient of several awards, including IFAC Nathaniel B. Nichols Medal and IEEE Control Systems Technology Award. He is Editor-in-Chief of Mechatronics. Please join me in welcoming Dr. Moheimani as he takes center stage in the spotlight. Dr. Moheimani, welcome.
Thank you, Tiffany. Well, good afternoon, everyone. I'm Reza Moheimani, and I'm very pleased to be with you this afternoon. It's a great opportunity for me to tell you a little bit about the Center for Atomically Precise Fabrication of Solid-State Quantum Devices, or for short, Quantum Device Center. This center was established last year by UT Dallas following a competitive process. The funding source for this center, as well as a number of other research initiatives in the university, come from the NROF money that the university qualified for a couple of years back. Objectives of this center are twofold. The primary objective is to develop new methods and technologies for fabrication of solid-state quantum devices. So the two keywords that are important are solid-state quantum devices and fabrication technologies. A secondary, but also a very important objective of this center is to function as an umbrella organization for everyone, all UTD researchers who are working in quantum technology. When the center was established last year, the center membership was drawn primarily from faculty members in Johnson School of Engineering and Computer Science. I think soon we realized that there was a lot of synergy between research interests in quantum technology in Johnson School and some of the research colleagues that we have in Department of Physics. I'm very pleased that we have now two new members from Department of Physics faculty members, and I certainly hope that we can expand the membership both in Johnson School and in other parts of the university. We certainly want to be inclusive and support all research activities and promote them, all research activities in quantum technology in the university. So why is quantum technology important? Why is it of interest these days? If you look at the history of manufacturing going back several centuries, throughout all those hundreds of years, there has been a constant theme to build devices and tools with better and better precision. We are getting to the point now that we can build devices, systems, and tools with nearly atomic precision. We can design systems in which every atom is where we want it to be. When you get to the atomic scale, nature starts behaving in ways that are a little bit different to what we are used to considering our experiences living in this macro scale world. Nature starts to behave in a quantum way. And it turns out that if we could harness those quantum properties of the matter, we can build new technologies, new devices, new tools that have quite important economic implications. You have probably heard about quantum computing. Quantum computing is one of the technologies that's attracting a lot of publicity these days. These are not computers that would replace the computers that we are using every day. Rather, they can, if we get them someday, we will be able to use them to solve optimization problems that takes a lifetime for computers that we have today to solve. I know that there are companies that are trying to use quantum phenomena to build radar-like systems. There's been a lot of progress in secure communications using quantum concepts. I'm familiar with the work that some groups are doing to build new imaging tools, biomedical imaging tools using quantum phenomena. There's been a lot of advancement in building new navigation devices that could replace GPS. There's a lot of interest in building gravity sensing devices using quantum concepts for mineral exploration, and also quantum timing devices. Each one of these, or many other applications that we probably can't think of today, could emerge as a success story when we use these properties of matter, quantum properties of matter. So is this the right time for UT Dallas to invest in a quantum center? And I think the answer is, of course, yes. Simply because United States is investing in this field, and so is every other developed country and some developing countries. If you look at the chart I have on the right-hand side of this slide, what you see here is the number of patents that have been granted in quantum technology over a period of 5 years. You can see that, judging by IP produced, we are clearly number one in quantum computing, so that's great. We are ahead of everybody else. But in other areas of quantum technology, we have serious competition. And I suspect, because of this very fact, United States government and Congress decided to invest in quantum technology under National Quantum Initiative that invests $1.2 billion of new research money into quantum technology research. Other countries are doing the same. The same initiatives are happening in Europe, Asia, and all over the developed world. So chances are that a lot of interesting technologies will emerge out of all this research. And it's not clear at all if quantum computing is going to be the killer app coming out of this field. It could be anything, but quantum computing certainly is getting a lot of attention, and there's a lot of activities happening in that area. Speaking of quantum computing, there are several approaches to building quantum computers at the moment. There are several companies that are investing in trapped ion systems. IonQ is probably the best known. There are several companies that are investing in building superconducting qubits. Google, IBM are two companies that are specializing in that area. The picture you see here is one of the latest quantum computers that IBM demonstrated. It can function with a couple of dozen qubits. Look at the size of this system. It's huge. It's big. It's bulky, and it's difficult. It's a very complex system. You have to cool it down to about 3 millikelvin temperature so you can operate it. So very close to absolute zero. And it's a difficult system to work with because it's quite big. Scaling this up is not an easy thing to do. There's an alternative technology which is based on this idea of silicon quantum computing. So here, the idea is to build qubits, quantum computer bits, out of silicon, on a silicon substrate. And what makes this technology attractive is that if you could build your quantum computer chip from silicon, then you can integrate that with traditional electronic systems that we have developed over the past many decades, and is fully compatible with semiconductor technologies that we have developed now and we are using on a daily basis. So there's a lot of interest in developing this technology further. And what you see in this picture here is a 2-qubit quantum computer, quantum device that was demonstrated last year by a group that is based in University of New South Wales in Sydney, Australia. This is a state of the art. At the moment, the best we have been able to do is to build 2 quantum computer bits using based on a silicon substrate. And there are groups in the United States that are trying to improve this. There's a group based in Sandia. There's another group based in NIST. Colleagues here in Zyvex Labs are working on this, and we are helping them as well. If you want to build a quantum device like this, what you need to do is initially, the first step is to perform lithography with atomic precision. What you can see in this picture is quantum qubits. There are 2 qubits, there's a left qubit, there's a right qubit. These are atoms of hydrogen that have been removed and replaced with atoms of phosphor that are placed 13 nanometers away from each other. That's the level of precision you need to be able to achieve and do lithography with. So the first step is to perform lithography on silicon with atomic precision. And a number of things go wrong when you want to do that. There's only one technology available at the moment that enables us to do this kind of lithography on silicon, and that's based on a scanning tunneling microscope. So I'm going to spend a couple of minutes explaining how a scanning tunneling microscope works, and then how we can use it for atomically precise lithography. So STM is an instrument that was designed to perform imaging on material surfaces with atomic precision. It was invented in early 1980s by 2 physicists who were working for IBM Zurich Research Labs in Switzerland. The concept is shown in this cartoon here. The idea is that you take a probe that's made from metal, typically tungsten. It should have a tip which is atomically sharp, and you bring this close to a surface that you want to image. The surface has to be conducting or semiconducting. You also need to establish a voltage difference between these two, a DC voltage, positive or negative, depending on the mode in which you want the STM to work in. What happens when you bring the tip very close to the surface, about a nanometer, is that a quantum phenomenon occurs. Electrons start tunneling from the atom, which located at the apex of the tip, to atoms on the surface in vacuum. Classical physics does not allow this. This is a quantum mechanical phenomenon that occurs. But this is something that quantum mechanics predicted for many years, but people found it difficult to demonstrate in laboratory. And the complication is maintaining a distance of a nanometers or less between these 2 large objects. Just to put it into perspective, that distance is 2 or 3 atoms of silicon. So maintaining that distance between these 2 objects in presence of noise, vibrations, and things like that is very difficult. So what these two gentlemen, these two experimental physicists realized was that they could use a feedback control system to regulate that gap. So what they did was that they measured the tunneling current using a transimpedance amplifier that takes that current, amplifies it, turns it into a voltage. And that voltage is then presented to a controller, proportional integral controller. And that controller moves the probe up and down using a piezoelectric actuator so that that current stays constant. So the idea of STM is that by regulating the tunneling current, we can regulate the gap between the tip and the surface. This animation shows how the STM works. You establish the current and then you move the tip over the surface in a raster pattern line by line. What happens is that the current wants to change, but the controller moves the tip up and down so that the current stays constant. And it turns out that if you plot the control signal, the control effort involved in moving the tip up and down as a function of position, you get an image of the surface. It's a three-dimensional image that you can produce. Now, STM is an imaging tool, but that's the only imaging tool we have, or at least we had at the time, for imaging surfaces with the atomic resolution. From the very beginning, people started asking the question, is it possible to use this technology to manipulate matter at the atomic scale? Can we move atoms around? Can we pick and place atoms on a surface and things like that? The first person who could demonstrate this was Don Eigler, who was a researcher based in IBM Almaden here in the US. And he did this work back in 1989. What he did was that he used STM's tip to move 35 atoms of xenon on a nickel substrate. And he placed those 35 atoms with atomic precision so as to spell out the three letters IBM. So this was very impressive, and this is the kind of thing that we can do very quickly and very efficiently today with the STM systems that we have. But it's not particularly useful if you want to build a device. If you want to build an electronic device, you have to do these things with silicon. And with silicon, it's a completely different story. The bonding between atoms of xenon and nickel is pretty loose, so you can easily move these things around with an STM tip. But with silicon, it's quite a different story, as I said. Now, it turns out that there is a way to manipulate silicon surfaces using STM. And this is called hydrogen depassivation lithography. So the way this procedure works, the idea is that you start with an atomically flat silicon terrace, and then you introduce atoms of hydrogen to the environment. Atoms of silicon that are on the top surface, they are highly reactive and they form a covalent bond with atoms of hydrogen. So what we have hydrogen terminated silicon. So we have on the surface now we have hydrogen, and underneath hydrogen we have silicon. Then the idea is to position the tip of the STM on top of one of these atoms of hydrogen, reverse the polarity of the STM system, and inject electrons into the bond between hydrogen and silicon. During imaging mode, typically the surface is negatively biased relative to the tip. When you are in lithography mode, the surface is positively biased relative to the tip. So electrons are now moving from the tip to the surface. What happens is that under the right conditions, under the right voltage bias and current, we can remove atoms of hydrogen selectively. So we can then move the tip to another location and remove another atom of hydrogen as we want. The next step is to introduce phosphine gas molecules into the environment. These silicon dangling bonds, the silicon atoms that are free and don't have hydrogen attached to them are now extremely reactive. And the rest of the hydrogen atoms on the surface function as a resist. So what happens is that those atoms of silicon that are free form a bond with these phosphine molecules. The next step is to heat up the specimen, and all of the atoms of hydrogen leave, and we get atoms of phosphor embedded into the silicon. And then what we can do is that we can cover these atoms of phosphor with extra layers of silicon on top of them. So each one of these atoms, each one of these dopant atoms that we have introduced into this crystal can now function as a qubit. That's how you build a silicon quantum device, a silicon quantum computer or a silicon quantum device. People have used this technology to build many devices. All of these devices that you see here were reported by this group that works in University of New South Wales in Sydney, Australia. Single atom transistor, few electron quantum dot, and many other silicon quantum devices that they have demonstrated with this very technology. And as I said, there are other groups here in the United States and in the UK that have exactly the same capability, and the group here based in Xivex Labs that we work with closely can do the same as well. But this is a difficult thing to do. Building these silicon devices is quite time-consuming. And the reason is that we are using a scanning tunneling microscope. We are using a tool that was designed for imaging and characterization, not for lithography. So the fact that we can do lithography with this tool is a very clever hack, but it's costly. You make many mistakes before you can build a device that works. A lot of things could go wrong when you use STM for lithography. So I'm going to mention a couple of these problems and how we managed to find solution to those issues. One of the very common problems that happens when you use STM for lithography is tip crash. Tip crash happens during imaging as well. And it's the kind of thing that's very familiar to all of the researchers who have worked with STM for decades, but it's the kind of thing you can live with if you have enough time on your hand. When you're doing lithography, it's a different story. Tip crash happens a lot more frequently and is more problematic. Basically what happens is that sometimes you lose the control of the STM and tip comes into the contact with surface. What you see in this image in the right, they were doing lithography on hydrogen terminated silicon, and what they wanted to do was to build a 2D array of square-shaped patterns. So there's one here, another pattern there, another one there, and there's another row and another row. So they spend a lot of time building this pattern, which is pretty large, and I think it's about 10 nanometers by 10 nanometers, each one of the squares. And then they suddenly lost the control of the STM, and the tip started hitting the surface and leaving these imprints on both sides. So when this happens, you can forget about the surface, the specimen is lost, you can forget, and almost certainly the tip is damaged as well. So this is a serious problem with STM, and a big problem that needs to be addressed if you want to turn this idea of hydrogen depassivation lithography into a viable fabrication technology for mass production of silicon quantum devices. So to understand what goes wrong, folks at Xivex Lab pulled out some of the tips that they managed to crash and put them under scanning electron microscope to look at them closely and see if they could understand what happens. And what you can see from these pictures, and they have many tips that have gone bad. What you can see from these pictures is that there's not a unique recipe that explains what the problem is. Somehow something happens. Some of the tips go inside, melt a piece of silicon and bring it out with them. Some of them are just, smashed to the surface and get dull, and then you cannot use them because they're not sharp. A lot of things goes wrong. So the question is, what happens? What is the problem, and how we can deal with that problem? So to me, John Randall came to me about 5 years ago and said, hey, Reza, can you help us find out what the problem is? And I started getting interested. And to me, from the very beginning, it was clear that if the tip comes into contact with the surface, something has gone wrong with the control system, because the purpose of the STM's control loop is to separate the tip from the surface and guarantee that we have a certain gap between these two objects. If the two objects come into contact, the controller has messed things up. So we need to find out what happens that this happens. To understand what happens, we need to look at the relationship between tunneling current. This is the current that goes between the atom at the apex of the tip to an atom on the surface, and delta, the tip sample separation. Tunneling current is an exponential function of tip sample separation. If I take log of both sides of this equation, then log of the tunneling current becomes a linear function of delta. Now, in STM, ideally, what we want to do is to measure delta and use a controller to regulate it. That is not possible. There is no way, absolutely no way, that we can measure that tip sample separation directly. However, we can measure the current, take its log, and then use a feedback control loop to regulate log of I. If I regulate log of I in a roundabout way, I'm regulating delta. That's the only thing we can do. Now, if the surface is uniform, so we have only atoms of silicon or hydrogen or gold or whatever uniformly over the surface, and if the tip is very stable, if no tip change is happening, then everything is fine. The STM will work really well. However, there are these other couple of parameters that enter into this equation that could cause issues. VB is the bias voltage between tip and surface, and that's constant. You provide a bias between these two objects, and you're fine. Sigma, we're going to assume for now that it is constant. We'll get back to it at a later point. Phi is the local barrier height. It's the average work function of the tip and the surface. It's a quantum mechanical parameter of the tip and the surface. If you tunnel electrons from the tip to one type of atom, as soon as you move to another type of atom, phi changes. Or if a tip change occurs, phi will change as well. So keep that in mind, because I will show you later on that these variations in phi is the thing that causes the feedback control loop of the STM to go unstable and for the tip to crash into the surface. What you see here in this block diagram is essentially what the STM feedback control loop looks like. So each one of these black boxes represents one of the important components of the scanning tunneling microscope. For example, GHFS represents the dynamics of the high voltage amplifier that drives the piezoelectric actuator. GPFS represents the dynamics of the piezoelectric actuator itself. It's a highly resonant system. It's flat at low frequencies, and then we have sharp resonances at higher frequencies. H represents the atomic structure of the surface that shows up as a disturbance in the feedback loop. So the feedback control loop here is a disturbance rejection control system. R represents the gain of the transimpedance amplifier that takes the current, turns it into a voltage. And K represents the dynamics of the feedback controller, which is typically a proportional integral controller with fixed gains. The way this control loop works is that we define a set point for the tunneling current that we want. We compare that with the actual tunneling current. We get an error signal here, and that error signal drives the controller. And the controller works in a way to reduce the error signal, ideally to 0. And when that happens, then we know that the tunneling current is equivalent to the set point that we decided we wanted to have. To study stability robustness of this feedback control loop and understand under what conditions the control loop could go unstable, which results in a tip crash, we need to have a model for all of these stuff here that are boxed into this new system that I call GFS. And to determine that, the thing to do is to do closed loop system identification. So we performed a number of experiments to determine the dynamics of this system that I call GFS, the STM transfer function effectively. Performing closed loop system identification involves injecting certain signals that you know into the feedback loop at certain locations and measuring the frequency response of the system at a number of other locations. And eventually you can determine a frequency response function for this system from this input to this output. Once you have the frequency response function, you can fit a model to it and you have a dynamical model. As soon as I have a dynamical model for G, I know what controller I have. I have a procedure to manually tune that PI controller. So I know the controller, I know G, and I can start analyzing the closed loop system and find out the reason that closed loop system goes unstable. One thing that we noticed during the experiments that we were doing was that same day, same sample, same tip, one experiment after another, we could see that low frequency response of the system G was changing over, and the range was quite significant. So for some reason, that low frequency gain changes. And if you look closely, you can see that square root of phi being local barrier high, shows up as the gain of this transfer function. So the cause of the thing that makes low frequency gain of G to change is variations in the local barrier height. And in fact, we were able to demonstrate that the changes in local barrier height were sufficiently large to result in an unstable closed loop system, which would cause oscillations and eventually crashing the tip into the system, into the surface. So then the question was, how do we go about solving this problem? How do we go about making the controller change in a way that could deal with these changes in local barrier height? Well, the idea is quite simple. If I can measure local barrier height when the STM is operating, either doing imaging or doing lithography, then I can change gain of the controller in a way that the loop gain of this system stays constant. So if local barrier height increases, I decrease the gain of the controller. If local barrier height decreases, I increase the gain of the controller. I can do this adaptively, and the requirement for that is that I can measure local barrier height somehow. So we came up with this process. What we do is that we inject a high frequency, low amplitude DITR signal at the input of the controller. So we add this high frequency DITR signal to the error signal in the feedback loop. And we use two lock-in amplifier to measure the response to this high frequency DITR signal at 2 points. One of them is W at the control output, the other one's at the output of the system, log of I. If you look at the transfer function from this input to W and Y, you can see that one of them is kg over 1 plus kg. The other one is kg over 1 plus kg. So if I divide these two, what I end up with, all of these things cancel out, and I'm left with g of j omega. And I know that gain of this transfer function is proportional to the local barrier height. So this signal here that I call C tilde changes in tune with changes in local barrier height. So when this signal changes, I know that local barrier height has changed. So in a way, this tells me what the local barrier height is. It's a number multiplied by local barrier height, in other words. So once I have the local barrier height, I can adaptively change controller gain so that the loop gain of this system stays constant. And because we can estimate the local barrier height a lot faster than the bandwidth of the system, we can update the controller fast enough so we can counter all of the issues that could happen when LBH changes. So we tested this method on a number of systems. What you see in this picture is one of the first STMs that we implemented this LBH estimation and adaptive compensation method. Initially, we implemented the control method in a D-space rapid prototyping system that we have. This is, by the way, a homemade STM system that folks at Zyvex Labs put together and works quite well, actually. And we did a number of experiments. This is one of the first experiments we did. So what we did here was that we started with an atomically flat terrace of silicon, and we passivated silicon with hydrogen atoms. So on the top surface, initially we have hydrogen, and then underneath hydrogen we have silicon. These orange rows that you see, they are atoms of hydrogen. They are dimer rows of hydrogen atoms. And initially, the entire image is orange because we have hydrogen atoms everywhere. Then what we did was that we moved STM's tip over one of the rows, started with this one, changed the polarity because we wanted to do lithography, and moved the tip over this dimer row on a straight line and injected the amount of current that we needed to remove hydrogen atoms. So this yellow line that you see now is silicon dangling bonds. So we remove hydrogen and now we have silicon. We did that with this row, and finally with this row. We did lithography on 4 rows. And then what we did was that we went back and did imaging, returned the polarity to negative, the imaging mode, and we imaged these surfaces. And we did it in 2 modes. The first imaging, the first one, this column, is done when the tuning is off. So we're doing conventional scanning tunneling microscopy. Controller gains are fixed. The second column experiments were done with this adaptive tuning algorithm functioning. What you can see, what happens when the tip moves, say, from left to right, as soon as we start going over these silicon dangling bond, the error signal increases quite significantly, which means the tip is oscillating, and the tip goes through these major oscillations, and it could actually, in fact, hit the surface. This is the thing that happens, that when we move over from hydrogen to silicon, suddenly that shows up as a major disturbance because there's a big change in the LBH, and those changes cause oscillations in the STM tip. But when we repeat the same experiment with our adaptive tuning controller, everything works fine. The error signal is quite very quiet, and the tip does not go through oscillations, and the chance of tip crash becomes very small. So we actually performed this experiment on many samples, but ultimately what we were interested in is to find out if this method could actually increase the lifetime of the tip. And to do that, we had to do experiments over long periods of time. So we performed imaging over 4 hours on the same sample. So these images that I'm showing you here are taken every 20 minutes, and we are continuously imaging. So between every 2 images, we have probably another 10 images that I'm not showing you. So the first image was taken at a time, the second one 20 minutes later, then 40 minutes later, then 60 minutes later. And think that between them, we are actually continuing to imaging. In the first set of images, we had this tuning algorithm functioning. So one thing that we noticed about this tip was that the tip was very unstable. A lot of tip changes were occurring, and all these stripes that you see in the images are the tip changes that happen. And tip change means change in local barrier height and potential instabilities. And every time that this tip changes happens, controller recovers because of this adaptation and protects the tip from crashing into the surface. So if you compare the first image that we have here with the image that we took 4 hours later, there's hardly any difference between the two. There's the natural slight drift that you can't avoid at nanoscale. But if you look at the features, the tip has not actually altered the surface, and that's what you want. When you're imaging, you do not want to change the surface in any way. Then we got to this point after 4 hours, we fixed the controller gains and started imaging the surface. Again, the same surface over and over again, but this time the controller parameters were not adapting, they were fixed. We were doing conventional STM. And as you can see, for the first 20 minutes or so, we are fine, but then we start altering the surface. So clearly the tip is messing up with the surface, either is touching it or is coming very close to it and depassivating hydrogen along the way. And ultimately it just crashed into the surface and just destroyed the surface, and the tip was destroyed as well. So by the time that we got here, we knew that we had a very good approach to dealing with tip crash in STM. By the way, I might mention that we patented this method, and it has been programmed into Xivector, which is a commercially available lithography control platform that Xivex Lab markets. Now, so the first problem that I think the biggest problem with using a scanning tunneling microscope for lithography is tip crash, and I think we've solved that problem. That problem is out of the way. There's another problem. When you're doing lithography, the conventional lithography with STM, one thing that happens very frequently is that inadvertently you depassivate hydrogen atoms elsewhere. So one example is here. They wanted to just depassivate a dimer row of hydrogen to reveal the silicon dangling bond. But when they did that, they also removed this 1, 2, possibly 3, 4 other hydrogen atoms elsewhere. So this spurious dangling bond formation and depassivation is something that you see when you're using a scanning tunneling microscope for lithography. So if you want to do good lithography, if you want to build atomically precise devices, we need to find a way to deal with this problem as well. So to show you how we solve this problem, I need to sidestep a little bit and talk about STM-based spectroscopy. This is the feedback control loop of a scanning tunneling microscope, very similar to the feedback loop that I showed you a few minutes ago, a little bit different though. There's a little bit more detail here. And the thing that I didn't include in the previous one was this bit. So in STM, what you want to do, you want to determine, when you're imaging, you want to determine H being the atomic features that you have on the surface, and you estimate them by plotting the control signal. So the purpose of this feedback loop is disturbance rejection in a way. Now, there are 2 other parameters that affect how this feedback control loop operates. One of them is phi. Phi changes, local barrier height changes, and it affects the operation of this feedback loop. We are fine with that. We know how to measure it. We know how to compensate for it. The other thing that could change is this thing that I represent as F here, and that's local density of states. So these two things, local barrier height and local density of states, are electronic properties of the surface that do affect how the STM feedback loop operates. And what it means is that when we are plotting the topography of the surface, what we call topography is not just the true topography, it's the topography plus these electronic properties that have been added to it. So from the very beginning, people became interested in extracting these properties, doing a spectroscopy. So phi we know how to do, we know how to determine local barrier height, and there is actually important information encoded in the LDOS that could be taken out. So to do that, what they do this thing that's called DIDV imaging. So the idea is basically that you look at the IV curve. So we are applying a voltage to the tip. We have a voltage difference between the tip and the surface, and we have a current going. You can model this as a resistor in parallel with a capacitor. Resistor represents the tunneling current that we have. Capacitor represents the actual capacitance that we have between the tip and the surface. So when we apply voltage, if the voltage is very low frequency, the current that we measure is pretty much resistive. But if we apply high frequency signal, the current that we're going to get is going to be a combination of resistive and capacitive current. So in DIDV imaging, you're biasing the tip at a certain voltage, and then you're measuring the current. Now, the idea is to add a high frequency, low amplitude DITR signal to the tip or the surface, depending on the way the STM is set up. So we add this high frequency DITR signal to the bias voltage. And the current that we get now consists of a tunneling current and a capacitive current. We can use a lock-in amplifier to separate the tunneling current from the capacitive current. And by measuring the amplitude of the tunneling current at that frequency and dividing it by the amplitude of the DITR signal, we can actually determine the slope of this line. This is called DIDV imaging, and it helps us produce an image that gives us more insight about electronic properties of the surface. One of the big issues with this method is that it's highly noisy. The image that we end up getting could be very noisy. DIDV images are very, very noisy. And there's a lot of interest in lowering the noise. So this is the typical kind of image that you get. On the left, we have the topography of the surface. On the right-hand side, we have the DIDV image. So in this case, the bias voltage was minus 2.5 volts. Set point current was 1 nanoamp. These are typical imaging conditions. Frequency of the DITR signal was 700 hertz. The bandwidth of the closed loop system is only a couple of hundred hertz. And the amplitude of the DITR signal is 0.1 volts. So it's a very small voltage. And of course, the signal that we get, the image that we get is very noisy, but nonetheless, it has important information about electronic properties of the surface that are quite useful. So how can we improve this? How can we get a better image? Well, what we can do is that we can increase the amplitude of the DITR signal. The problem is that if we increase the amplitude of DITR signal, of course, we get a DIDV image, which is good now, because the signal is increased, noise is at the same level, so signal to noise ratio has gone up. But then we end up with a topography image which is noisy, and the reason is that this signal, although it's out of bandwidth of the control system, nonetheless it finds its way into the closed loop and it starts disturbing the feedback loop operation. So how do we deal with this problem? I had this idea that all I needed to do was to add a whole set of notch filters into the feedback loop right after the transimpedance amplifier. If I do that, basically what I can do is that I can separate this high frequency jitter signal and its harmonics from the rest of the feedback loop. So typically what we do is that we have 4 or 5 notch filters tuned to the fundamental frequency, the same frequency of the jitter, and its first 3 or 4 or 5 harmonics, the harmonics that are substantial. And that way, those high frequency currents are actually going between the tip and the surface, but the feedback controller does not see them because they're actually completely removed at that point. And as far as the STM is concerned, it's in the imaging mode and everything is working normally. But because of this new set of notch filters, I can increase the amplitude of the jitter signal, and I can measure current at much lower noise level, and I can produce a very good DIDV image at the same time that I can produce a very good topography. So this is the kind of thing that in itself is very, very useful, and it helps people who want to do spectroscopy based using STM with a very high precision and high accuracy. But then the question, of course, that we had was, can we improve it? Can we use this for other purposes? And it turns out there's a lot of useful things that we can do when we make this a small modification to the STM feedback loop. One thing that we could do is that instead of using the STM to regulate log of current, we could use it to regulate log of DIDV. So we could close the feedback loop on measurement of DIDV. And this is something new. This is something that no one has done before. And the reason that it works is actually shown in these equations. If you look at the current is an exponential function of delta, delta being the tip sample distance. And F is the local density of the states, which is a function of voltage and a few other parameters. DIDV is still an exponential function of delta, and here we have dFdV. So if I take log of both sides of this equation, I have log of dIDV is now a linear function of delta. So if I close the feedback loop on log of dIDV, and regulate the log of dIDV, I'm regulating delta. It's the same as conventional STM. The subtle difference here is that in conventional STM, the effect of local density of states appears as log of F. In this new method, it appears as log of dFdV. So the images that we get, the topo images that we get, are slightly different. And in fact, you can see that here. The image on the left is the conventional topography. The image on the right is this new what we call AC mode topography. It's clearly the same surface, but there are very visible but subtle differences between the two images. And we need to do a little bit more investigation to fully understand the significance of these changes and what they tell us about the electronic properties of the surface. So this is all imaging and characterization. But what about lithography? We are really interested in doing atomically precise lithography. One of the questions we asked from the very beginning was, what happens if we repeat this experiment, but this time increase the amplitude of jitter signal quite substantially? So we did an experiment. The bias voltage is -2.5 volts. Set point current is 1 nanoamp. Typical imaging conditions for hydrogen passivated silicon. And but then in this case, the jitter signal has an amplitude of 2 volts. This is the conventional image before we actually add the jitter signal. Then we add the jitter signal, do imaging, and did another imaging after that. And this is what happens. It was clear that we had removed hydrogen atoms quite randomly. So it seemed like there was a possibility to use this method to do lithography. So we did a number of experiments. One thing we did was we started on a hydrogen terminated silicon surface, positioned the tip at that point, and then moved it along this straight line on a dimer row. We also added the DITR signal and ramped up the amplitude of the DITR signal as we moved on the dimer row. And you can clearly see that we get to the point where we start depassivating hydrogen. And what happens, we can actually, if you look at the current signal, we can actually see that there are spikes in the current signal. Basically what happens when an atom of hydrogen leaves the surface, say here, it reveals a dangling bond underneath that. It's a lot more conductive, so the current increases immediately. There's a step change in the current, and the feedback loop reacts to that by pulling the tip away to lower the current, because the feedback controller wants to regulate the current to the level that we set up. So we see this type of spikes when we look at that, and we can clearly see the point where this depassivation happened. And it looked like we could clearly remove single atoms of hydrogen. So we actually turned this into, we automated this process, and we can actually do exceptionally accurate atomically precise lithography on silicon. What we wanted to do here, you can see the before and after lithography images. We wanted to remove 9 atoms of hydrogen, and we did this one by one, and you can see the process that we had on the right-hand side. It is extremely difficult to do something this accurate with conventional hydrogen depassivation lithography. It's next to impossible. But this method actually allows us to do this very cleanly and very, very accurately. So again, we have a provisional patent on this that I understand Xivex Labs is going to license from us. A few other things that we do before I wrap up, apart from developing methods for controlling the STM and making the STM work more accurately for hydrogen depassivation lithography, we are actually working to completely change the electromechanical components of STM. We are building MEMS devices that can replace the piezoelectric tube scanner that STMs use. You can see the first generation that we have incorporated into a ultra-high vacuum system in Xivex Lab, and we've been doing some promising experiments with this MEMS device. The nice thing about this is that you can array them and use them as an array. You can stack them on top of each other, use them as an array. We are also developing new cantilevers, AFM cantilevers, that allow us to combine non-contact AFM with STM, similar to the Q+ technology that some of the manufacturers of STM are using. The nice thing about this technology, again, is that we don't have to limit ourselves to just one tip. We can actually use an array, and these cantilevers have actuators and sensors built into them, so they can operate independently. Before I finish, I should acknowledge the funding that I've received for this research. UT Dallas has been supporting me for the past 5 years. DARPA, Air Force Research Lab, Xivex, we've worked with them very closely, and we've been getting a lot of support from US Department of Energy recently. I'm very lucky that I've had the opportunity to work with very talented young men. These are my PhD students and postdocs. Some of them have left now. Farid, Bulut, and Mohammed are in the West Coast working for companies like, I don't know, Amazon and JPL and Apple, and Afshin and Hamid are still doing their PhD with me. We also work very closely with colleagues in Xivex, John Randall, James Owen, and Udi. We work with them very closely, and Josh Ballard, we worked with him, but now he's left and he's somewhere else. That's all I have to say. Thank you very much.
Dr. Moheimani, thank you very much for your time today and for sharing all of the information you did about your center. For those of you that did attend, thank you very much. For additional information and Office of Research events, please visit research.utdallas.edu. Have a nice afternoon.